Okay, so we just looked at magnetic flux. So next, Faraday came along and he said that the EMF produced, which is directly linked to current as well, is proportional to the change in this flux over time. So what he discovered was that EMF, this is our EMF, so basically voltage, is equal to delta is change, so change in magnetic flux over delta T. So again, remember for flux, we're talking about the amount of the magnetic field passing through a given area. And for circuits and electricity, we have these things called solenoids, because what they also discovered is that if you have the multiple loops like so, it just is going to be amplify that EMF. So you get EMF is equal to N over multiplied by the change in flux over time, where N is the number of turns. Now the question is, why is there a negative? Because what's the guy called Lenz later came along, and he discovered that the induced EMF always leads to a current whose magnetic field opposes the change in flux. So it all comes down to Newton's third law. For every action, there's an equal and opposite reaction. So like the world wants to stay as it is. So along comes this magnetic field. The current and the EMF that's produced is going to oppose that change. So again, the calculation-wise, straightforward. If you know the magnetic field and you know the change in magnetic field in time, you find a voltage. So let's see if we can just go over the different scenarios. So the tough thing is always about, like, is it going to go clockwise or counterclockwise? Like, which way will the current travel? So let's scroll down. So we have a couple different examples right here. Okay, so let's say we have a north and south magnet. So we know that from before that if we can draw magnetic field lines coming from this magnet. So for example, there's going to be field lines coming from the north, and they loop around to the south side. And they loop around to the south. Okay, so our magnetic field looks something like the following. So the question is, if this magnet is traveling towards the solenoid, so we're going to say that we're going to bring this closer. So we're going to have some velocity to the left. So right now, what we can kind of think of it as is, let me just draw it over here. When the magnet is far away, we're going to have fewer magnetic field lines passing through. But as we bring that magnet closer, you can see that those lines, it's going to more of those magnetic field lines are going to pass through. So as we move this north-south pole, this north pole closer, more like that we're increasing the strength of the magnetic field through the solenoid. So more and more magnetic field lines are coming through. But Lenz's law says that the current that's going to be induced is going to oppose that change in magnetic field. So the magnetic field is getting bigger to the left. So this solenoid is going to create a current that's going to oppose that. So basically what happens is we get what's called an electromagnet. The solenoid is going to act like a magnet. So to oppose that magnet that's moving closer, this solenoid, this is going to act like a north pole and this is going to act like a south pole. And then if we use our right-hand rule, or this is the right-hand rule, is if we take our thumb and make a fist, here's my thumb, and my finger is going to curl around like so. Right? Okay, so there's my hand, and my thumb pointing that way, my fingers are curling around. We can see which way the current is going to travel. So in this case, the current is going from behind and over. So our right-hand rule is for the solenoid to act like a magnet, we need to create magnetic field lines that are going to oppose. We're going to oppose this incoming magnet. So our current is going to travel in this direction around the solenoid. So again, the current's going to travel like this. Current's traveling through that solenoid to oppose that change in magnetic field. Let's look at a few more examples. Okay, this can be a little tough. So let's see what happens if our north and south pole, but this time our velocity is moving this way. In this case, the magnetic field is getting weaker, so the less and less magnetic field lines are going to pass through the solenoid. So the world is saying like, nah, we like it the way it is. We don't like change. So this side's going to act like a south pole, and this side's going to act like north. It's going to kind of draw it back in. And I'm going to use my right-hand rule. So for this right-hand rule, my thumb is going to be pointing towards the north, the solenoid. And those are my knuckles. And you can see that, okay, our current is going to go in the opposite direction. So the current's going to travel in the opposite direction. So around, like so. And if we have a south and north pole, our velocity is this way. Again, here's our magnetic field lines. Let's move it. The magnetic field lines, the amount of quantity of lines that are passing through is going to get stronger and stronger. And the easier way to think of it is that the world wants to stay as this. This side's going to act like a south pole to oppose that change. It's going to try to keep it away. This is going to be a north pole. So once again, the current is going to travel in this direction. And we're going to get a right hand. We're talking about conventional current. Talking about conventional current, the flow of positive stuff. So again, in reality, the electron flows in the opposite direction, but again, as long as you stay consistent. And lastly, if we look at our south and north poles right here, and say if we now bring that magnet away from it, the magnetic field lines through the solenoid is decreasing. This side's going to act like a north pole, and this side's going to act like a south pole. The current's going to travel in that direction. So hopefully you have a chance to set this up in the lab. Just a very quick little demo where you just set up a solenoid, connect the galvanometer to it, and if you just move a magnet through, in and out through the solenoid, you'll see that the current will bounce back and forth, positive, negative, positive, negative. If you have multiple, if you stack some magnets together, like to make a stronger magnet, you can see that it'll increase the current greater as well, because we know that stronger the magnetic field, the greater our flux will be as well.